Last week we created the script to create a truss structure on Dynamo. So let's check it. As you can see, I get my 10 bar element truss outlines, and I get it at the end as a list from the lines. And my list has 10 elements also, since I have 10 elements in my truss. So this week we're gonna create a connection between robot structural analysis and Dynamo to import this truss to here and create all the elements on robot structural analysis software. To do that, we need a package named structural analysis for Dynamo. If you don't have this package, you can download it from packages, sort package, and typing you should type structural analysis for Dynamo, and you should download or install this structural analysis for Dynamo package. After that, you will have access to all necessary nodes. Now, first step is creating these elements on my robot structural analysis software. How I'm gonna do it is, I have analytical bar by the lines node. As you can see, the input is lines and output is analytical bars, and my input will come from the list that I just created. So I'm connecting this list to here, and I am having lines created on robot structural analysis software. As you can see, 10 elements. But here we need to assign them sections, materials, releases, at least. So how we're gonna do it is, we're gonna use analytical bar set section by name node. So here this node has analytical bar inputs, which is coming from here, because we create all the analytical bars. As you can see, it has ID, first element, ID1, start point, end point, and the coordinates, and second element, so on. So I connect them to here, and I am using level 1 for the list, because I want to take them one by one. And the second input is name, which is string, as you can see. So I have to give the section names as a string. Here I have a section list that contains 41 elements. First things first, these elements has to exist on your robot structural analysis template. As you can see, I have all the sections that I have written here. If you don't have them, you can basically import them by using robot structural analysis database from this icon. After importing them, you should use this node to see if everything is okay. So if Dynamo can access your sections, it will create a list by using this node, and you will see all the elements here. As you see, 41 elements and 41 elements. So all of the elements, all of the sections exist in my robot structural analysis. And I need to get items from these 41 elements, right? Because I have only 10 elements in my structure, so I need to get 10 elements from this list. How I'm gonna do it is, I'm gonna use inputs. So I will write some section indexes here. Based on these indexes, I will get some sections from this list, right? I did it. And as you see, I get 10 elements, 10 sections for my 10 elements. Now I will flatten this list, and I will connect it to the analytical bar by set section by name node, again with the level 1. And after running the code, it will create my sections. I'm using level 1 because I wanted to get first element from this list, first element from this list, and create the sections. As you can see now, my first element is this one, and the section is supposed to be this. Let's check it here, same section, right? So we have created our sections on robot structural analysis. Next step is we need to assign material, right? Again, it has input as a analytical bars and a name of the material, which is string, and I'm using S231. Again, your materials should exist in your document. As you can see, here is the all available materials I have in my template, and I choose S235. Alternatively, you can use materials nodes, and you can see all the available materials in your folder, You can choose it from here too. It will give you a string, but I prefer using code block and connecting it to here directly. After this one, my materials has been assigned, and you can see it here. My material is now as 235, and you can see the material properties here. Okay, next step is defining the releases. As you know, we are creating trusses, and the trusses don't have moment in the connection points, so it has to be pinned, right, in the both ends. So I need to assign these and these points as a pinned. As you can see here, there is no releases right now, and if we assign them pinned by using set release by name, and my name is pinned, and my analytical bus again coming from here, and run it. Now I have the releases pinned. You can also use pin fixed or fixed for these settings. Depends on your project. And as you see, it changed as a pin fixed. But since we are using a truss, I'm gonna use pin for both ends. And after assigning the end releases, now we need to assign sports, right? So I want to put two sports to here and two here, 1 and 4. Okay, so how we're gonna do it is, let's make a reverse engineering here. So what do we need is we need a sport, and the input nodes for this sport is nodes and name. Okay, so I need nodes. How can I get nodes? How can I get nodes? I can use analytical bar start node. So I will get this bar, then I will get its start node, right? And it will give me the analytical node. I will give it analytical bar, and I will connect it to my sport by name nodes. The second input is name. So the name is defining the type of my sports. So I want pinned and pinned sports for both ends, and I am giving it as a text string to my list. So I have two sports, and I have two names for these sports, and I need to get the bars to get their start node. So this one is this element 0, because as you remember, on Dynamo the list is starting from 0. Even though you are seeing 1 here, it is actually 0, and I need to get the third element, because I want to put the sports at the start point of these two elements, right? So I'm getting these elements from analytical by lines. So we create the elements here. I'm getting these elements, and I'm getting the first and third element from this list. Then I am letting the script to run. As you can see, now we have our sports at the points that I defined, and they are pinned. Now you can see it more clearly. They are pinned sports, right? I am having two nodes from here, ID1 and ID4, ID1, ID4. I'm connecting them to my sport by name with level 1, because I want to get first ID and connect it, create a sport with first name, and get second ID and create a sport with second name. You can change this one from here. If I change this one to the fixed one, now my sport become fixed and pinned. You see, one is fixed, one is pinned, but I want it as a pinned. Now I have pin sport. Okay. Now we have our sports too. What else do we need for this structure is loads. So I'm gonna have two loads for this structure. One is self-weight, one is the point load on the nodes number 5 and 6. Let's start with self-weight node. Okay. So first I'm defining the nature and case name of my weight, which is that and self-weight. Then I'm creating self-weight load. Let's see it like this. Okay. So as you see here, right now I don't have any weights or loads. So I am connecting this nature load case with self-weight load, create self-weight, because it asks my its input is load case. Then I'm creating load self-weight load, and after running these nodes, I'm gonna get as you see here, I got self-weight load. Now I want to create a point load, and I need to create again load case. This time my case nature is that again, and my case name, let's say it is FC1. Okay. Now I need to use node load by nodes node. So here there's some inputs. First, I need to define the value for the direction that I want to put the loads. My direction is minus z axis, and the amount is this one. Okay, I'm connecting it to here. Then next thing is I need nodes. Similar to the sports, I am getting the nodes from the bars. I'm getting element 3 and element 4, and this time instead of start node, I'm getting the end node because their end node is 5th and 6th. Right? So, and then I'm connecting this one to the analytical nodes input. The last one is I need to create load case similar to here. So I am having that and FC1. I'm creating a load case and I am connecting it with here. So let's run the code. Yeah. Here, as you see, now I have two load types. One is self-weight, one is FC1. And here, as you can see, we have the magnitude, right? And its direction, and on the 5th and 6th north. Okay. Now, after creating all these inputs, all these informations on the robot structural analysis, the script is ready for run. How I'm gonna run it is, I need to use element composer and connect all the informations that I create this orange group to here. So I need analytical bars, which is coming from my materials, because that was the information that I need. I need analytical nodes for the sports. I need load cases that I created here, two load cases, and I connect them with a list. Load case 1, load case 2. I created it to here. Nodal loads. Here, my nodal loads is here. Load ID, case name, nodes, and its magnitude to here. And self-weight load to here. Okay. After this one, my structure is ready for analysis. Let's run it. Okay. So after this one, I need to connect this element composer with elements from analysis node. So here parameter is name of my file that will be saved, and the directory path is where I want to save my document, the robot structural analysis document. So after analysis, it will save it to some location. Right, after that we are getting some dictionary. Okay, now after this step we need to get the stresses, the subweight, and the deformations, right, as a last step. How I'm gonna get the stresses is I'm gonna use bar stresses get max value list. Okay, so the here name is fxsx. We want to get stresses, and load case ID is coming from here fz1, because I want to get the stresses caused by my nodal loads. Okay, if I want to have the combination of them, I need to give two load cases here, but I want to ignore the set weight right now. After that, I am getting the set weights, and also I need to connect the analytical bars to here. I'm getting set weights, I'm getting bar stresses for every elements here. Okay, then I am converting it to the Newton divided by millimeter square. Right, now we can check if the results are correct. As you see here, so both of them for number 1, as you can see, the values are consistent, right? And I get these values through Dynamo. Now, similar to that, I can extract the subweight. Again, for the subweight, I need to use the load case for subweight load case. It's coming from here. I'm connecting it to the node reactions. Right, I'm getting the node reactions from the sports. Then I'm getting the FZ value. I'm converting it to the kilogram, and I'm having the value. Here, let's see. Mass is 1158, 1158. You see, by using these nodes and getting the node reactions, I'm getting the subweight. So next is extracting the deformation. Similar to the last steps, I need to connect analytical bars, load case. I just want the load case, the deformation caused by my nodal weight. That's why I'm just using the second load case, and the position of the value, position of the deformation. So since this is the trap element, we only need to see the deformations on the nodes. That's why I'm just choosing the end place of the elements deformation. So I'm getting the deformations, displacement in Z axis. I'm getting the displacements and converting them to the millimeter, and having the all deformations caused by my point load. Okay, after having these three information, I can say, okay, this structure is good or not, but I need to evaluate it, and I need to assign a number to this quality, to quality of structure, right? I need to know how good is this structure. Is it really good or bad? How I'm gonna know it? To know that one, I need to evaluate these results, right? So here I have a Python code which uses evaluation method, and okay, here I have a Python code. Okay, so we are calling this number. So as we said, we need a number to evaluate this structure. We are calling this number as a fitness value or penalized weight score, right? In optimizations, structural optimization, we have an objective. And in this scenario, let's say we want to have minimum value for this truss with minimum weight value for this truss. Okay, so our objective is getting a minimum weight from this structure, but we have some constraints, which are the stresses. We don't want the stresses to be higher than some amount. Also, we don't want the displacements are higher than some amount, right? So how we gonna evaluate these results and get an objective value? There's different methods for this operation, which are called constraint handling. And here we are using penalty function method in this Python code from Rajev. So basically, what we are doing is we are defining some constraints. Okay, so let's say for my tension stresses, the highest value should be this. My compression stresses, the highest value should be this, and my allowable displacement is this. Now I'm creating a code. It calculates which elements are not suitable for these constraints and violating these constraints, and then by considering the violation amount, it assigns them some penalty value. It adds some penalty value to my original weight. Okay, so that's how at the end I'm getting a number. This is my weight score or fitness score. So if, as you can see, my weight was 1,158. Now it become 48,000 because some of the values in my stresses, as you can see, and in my displacements, they are higher than the values that I want. So I'm assigning more weight to this structure to show that it is not the structure that I want. It is actually a bad structure, not suitable, not fit for my needs, right? I will share this Python code with you guys. You can find it in the documents. And by knowing those script, now you can perform structural analysis and you can know your weight score of the structure. As you can guess, if there is no violation, there is no additional penalty value to add to my original weight. So the weight score will be equal to my weight. From there, I will understand that, okay, there's no violation and all the elements are suitable for my constraints. That's enough for this lecture. Next step is performing a structural analysis by using these knowledges.